Do we start?
Yeah, you ready?
Yeah. Did you click record?
I did click record.
Okay. Okay, let's quickly recap. As I always write in the beginning of all the lectures, we were studying the scalar field with phi-4 interaction as a model for Ising model in d equal to 4 and above. And we performed all the steps of renormalization group to figure out how these couplings, one of them relevant coupling in the infrared and one of them naively marginal coupling in the infrared in d equal to 4, to see how they change. We did all these 3 steps, and then we actually found how they changed. Last week we did it for d equal to 4 minus epsilon, for epsilon very small. So in this case we made some variable changes. Let's recall what that is. So we defined x to be some number times lambda, which is the cutoff. So the cutoff is here, times this lambda, and y was lambda to minus 2 times u square. These are just rescaling to make it dimensionless. And then we found some differential equations for how these things change as we increase zeta, or as we perform RG, meaning as we go high to infrared more and more, how these coefficients run. We found it using using the results from these 3 steps. And I'm just going to write down the result for general case. So we found that dx by ds, where zeta was e to the s, was some beta x of x and y, and dy ds was some beta y of x and y. And then we looked for fixed points where the x and y do not change. So fixed points is when dx by ds and dy by ds are 0. So we need beta x of some x star y star equal to beta y of x star y star equal to 0. And near a critical point, we linearize this differential equation. X equal to x star plus delta x, y to y star plus delta y. And we got a result which was correct qualitatively, but I messed up some numbers, which we speculated in the beginning of last lecture itself, because when we found the renormalization of lambda, I forgot to pull out this 4 factorial, and that was a mistake. And I thought that's an innocuous mistake that it's going to not matter, but it's going to matter today when we actually quantitatively compute critical exponents. So rather than going back and fixing the mistakes, I'm just going to tell you that there was a mistake, and I will write down the correct numerical answer. So nothing qualitatively changes from last week. It's just that one of the eigenvalues just changed. That's it. So near the critical point, we had d by ds dx dy equal to minus epsilon 0, 1, 2 minus epsilon by 3 delta x delta y. So this was the numerical mistake last week. This is the correct answer. I leave it as an exercise, of course, because it's not worth going back and doing the numerics. And from this, what we did is just diagonalize. For example, if we take epsilon to 0, then we are working in 4 dimensions. So you can look at the 0, 0, 1, 2 matrix and diagonalize it and find the flow. And we'll do the diagonalization again today, but just for recap, let me just draw the flow from last week. So we had for d equal to 4, there was this line.
So the x star, y star is the non-zero fixed point? Is that right? Or the
X star, y star is the critical point.
okay.
So yeah, I should write it down. So there are, when epsilon is not 0, there are two fixed points. One of them is trivially, well, from this you cannot see, 0, 0 was a trivially fixed point, but there was another fixed point. And I think last week we saw that it was the other fixed point, which we call the Wilson-Fisher point, that had only one relevant direction. But the Gaussian 0, 0 fixed point had 2 relevant directions, meaning you cannot reach it by tuning one external parameter, right? You have to tune 2 external parameters to reach it. In typical experiments, you tune only temperature, which is just one parameter. So in any typical experiment, you should be just reaching Wilson-Fisher point. So the Wilson-Fisher point is the critical point where correlation length goes to infinity. So let me just write it down. X star, y star is critical. For epsilon equal to 0, the critical point merges with the Gaussian fixed point, which is what I'm going to draw now. So for epsilon equal to 0 or d equal to 4, epsilon equal to 0, we had this line that we found was irrelevant, meaning you start from that line, you just flow back to the origin, but then the y direction was unstable because you can see the y direction has an eigenvalue that's positive. So when you solve for delta y, you'll get delta y of s is e to the 2s delta y at 0. The solutions also we will do again today. So just for completeness, let me draw the pictures and then we just fill in the picture. So if we start anywhere here, just follow the flow. And if you start anywhere here, you go the other way. So we identified this to be the disordered phase where y is positive, meaning mu is positive, meaning the expectation value of phi would be just 0, or the minimum of the potential will be at 0. But this we identified when mu is negative, the potential will have 2 minima, and one of them, in either of the minima, you have non-zero value of average magnetization, which is ordered phase. Right, so this is order, and this is disorder. Now, we also looked at epsilon not 0 in d equal to 3.999. We found that there is a point here, but that was unstable. And there was another point which is very close to 0, but I'm going to draw it far away from 0 for visual purposes. The point was, proportional to epsilon. As you take epsilon to 0, it just goes to 0. And the point was along this line that we drew. And that point had the property that things were attracted to that point in this direction, but were repelled from that point in this direction. Once again, I will derive this one more time today. So don't worry if it's not immediately clicking from this equation. So we just then fill in the flow. This was the Wilson-Fisher point. So we then speculated that as we increase epsilon to higher and higher values close to 1, where we would be getting d equal to 3, we speculated that the qualitative behavior of the critical point doesn't change. The actual point might become somewhere else, but the qualitative features doesn't change. And when we actually tune temperature, which is y, in an experiment, we are actually just, say we are decreasing it and we actually hit this line and then we converge to that point. So in a 3D experiment, we speculated that we might be hitting the Wilson-Fisher point. So to see if it is actually somewhat true, we will compute something quantitative, which are these critical exponents, which people measure or numerically compute in these models, and see if that tells us something.
You also, for E equals to 4, you had just one critical point, and I think you made comment that there is only one direction, or there are multiple directions from that point out, right? And that corresponds to 2 parameter
for this one. So if we are at this point, which is the critical point in d equal to 4, but at d equal to 3.99, from this point you have this relevant direction and that relevant direction. So to hit this point, imagine just tuning the temperature down. If you hit this line, you flow to this line under Rg. But if you want to hit this point, you have to tune an additional parameter to.
And that is also a critical point.
This is a fixed point, yes.
So fixed point is that for which it's 0, what you have written.
So for d equal to 4, fixed point is here. For d equal to 3.9, you have 2 fixed points. And out of which one of them only have one relevant direction. Because we only have one tunable parameters, we want a fixed point with one relevant direction. Right? Only that point we can hit by tuning one parameter. So are we hitting this critical point in an experiment or not? We have to actually check against some numbers, which we'll do now.
So, but in the graph, you go to that line and then there's this flow that takes you to the critical.
Yeah, this flow is the Rg flow, right? So imagine that you have some microscopic system, but you're looking at it from some low energy. You're only probing it at some low energy. So roughly speaking, you would always flow to a critical point. If you are here, you would just flow to, very large y point, which is disorder. which should be taken in a qualitative sense. Yes.
So in the d=4 case, we have the one fixed point, and it has it has one relevant direction, or is it
One relevant.
one relevant direction and the other direction, is that irrelevant, or is that marginal?
It's marginal at this order.
Marginal linear order.
Yeah, but at the next order you would see it to be irrelevant, because the differential equation had just minus something squared.
So when you say relevant,
No, that was the question.
so when you say relevant direction, it's the direction that takes you to the point.
No, relevant just means, from this naive scaling things we said, if, for example, mu under just this steps becomes zeta square, 0 square. So under scaling, just scaling, mu becomes larger and larger. But for example, had we wrote G6, 5, 6 term here, then G6 of zeta would be zeta to some, negative power G6 of 0. It's irrelevant, yeah.
So I'm saying like on the graph, when you say direction, relevant direction, what does that?
I see. So this graph is the space of all couplings, right? So it includes mu, lambda 0, G6, all the infinite couplings. But I don't have to worry about all the infinite couplings because everything is just irrelevant. So imagine this is an infinite dimensional graph, but no matter where you start, you end up in this plane, right? Because everything goes to 0. Now, in this plane, we are left with these two couplings. And by doing these two steps only in d equal to 4, we find that this is marginal, meaning it doesn't change. But after doing all the steps, we find that this is also irrelevant. So no matter where you start in this infinite dimensional point, you end up in this line after doing RG. So you only have to tune this line to hit the fixed point, which is the critical point. So that's what I mean by relevant direction. It's not a direction of space or anything. It's the direction in the space of all coupling constants. Or we can just call it theory space. That's how David Tong calls it.
Can it be a combination of different coupling constant, or is it always there?
Yeah, for example, this direction, right? We called it's irrelevant. But that's not either x or y. It's a combination of x and y. So it's in general a combination. But in this case, we have one that's a combination, one that's not a combination. Same goes here. We have one that's at the Wilson-Fisher point, we have one that's a combination and one that's not a combination. But I guess if you do higher order perturbation theory, even that would change. In this case, I'm not sure. It should in general, I think. Right. So we discovered that there is this point, but are we hitting it or not in an experiment? So to get some clue, we'll just compute quantitative things and see if it tells us something. That's where this critical exponents that we discussed way past in the first lecture comes in. I know that none of us remembers it, so I will go through it one more time, but I don't have to, it's not wasted time because I will go through it while deriving relationships between critical exponents. So the idea is, in all of this discussion, the most important concept was scaling. And it's no surprise that these critical exponents can be related to each other via scaling arguments, which is what we will do. So first, let's imagine that we are sitting at the critical temperature. then we know that the correlation length must diverge, right? We recall that thing because from experiments we know that we see correlations at all length scales. So we must identify a fixed point with correlation length. At a fixed point you cannot have length scales. That thing we established at some point, because it's not changing under renormalization group. So you're changing length dimensions, but nothing is changing, meaning you cannot have length scales. But from experiments, we identify, C can be 0 or infinity to have no length scales. But we identify from experiments that this is the critical point. And if this is true, then if we compute, for example, the 2-point function, it can be nothing else but a power law, right? So you'll just parameterize it as 1 by x to the d minus 2 plus eta. It's a power law. D minus 2 comes from naive dimensional analysis. We'll see that soon. And eta is a parameter that we will have to compute. So eta is one of the critical exponents. Well, I'll just make a table. Critical x. So we have from 2-point function, we have eta.
So if d minus 2 makes up the dimension,
What makes up the eta dimension? Yeah, it's secretly, 1 by lambda.
Okay.
So where this thing extra comes from is where, when we do this step, for example, when we do the third step in the RG, we are actually, rescaling the units of phi. So when doing that, this gamma will have some units and the dependence on, cutoff, and that just gets absorbed into the definition of phi itself. So we would naively think that dimensional analysis is failing, but it isn't. But it's just convenient to forget about this guy and imagine that dimensional analysis is failing. So this is secretly there. Is that the correct argument?
I don't know, this is the first time I'm seeing that.
Okay, I think that's the correct argument. Yeah. So
Wait, so you say there's no length scales, but we do technically have lambda, right? Yes, okay.
Yeah.
We also have u at the fixed point. It also gives us the length scale.
mu at this fixed point.
That's a non-zero thing.
Yeah, that thing we talked about last time, right? Yeah. Yeah, it should be a length scale less theory, but at this point you shouldn't trust this thing. That's the idea.
Yeah.
I think that was the conclusion that we made last time.
Yeah. Well, I guess whatever that is, mu at the fixed point, it's just going to be some dimensionless number which we calculate in here times 1 over lambda.
Yeah.
So
Yeah.
only capital lambda.
Yeah. Still only, the capital lambda, well, even though we don't have length scales, it should be understood as a failure of this theory is denoted by the capital lambda. So when we say that there are no length scales, well, you shouldn't zoom in to the cutoff scale. If you're zoomed out far away from the cutoff scale, then you feel like there is no length scale. I think that should be the correct way to think about it.
And sorry, what was the interpretation of mu being there but not the length scale?
Right, so y has some non-zero value here, right? And y is, then mu would be some numerical number times at the cutoff. So cutoff is the only scale again, I think. So mu here is non-zero, but it's determined by, the scale is determined by the cutoff only. If you move away from the critical point, then the scale is determined by the temperature. So just like here, only cutoff is the length scale. Another not satisfying explanation is that at this point, you do not trust this. Even though we started off from this and discovered that critical point, you know, as Gary was saying, we applied perturbation theory where it's not applicable.
So you see, I mean, in the first argument, you see is a function of lambda, big lambda.
Which one are you talking about?
The fixed point.
Oh, at the fixed point, yeah.
You see whatever that value is, we can't find it from RG because we don't know the microscopic theory.
Yeah.
So it's a function of lambda.
Yeah.
That's what they're saying.
Yeah. Even though we cannot find the values of mu itself, it turns out the scaling arguments are enough to compute this critical exponents.
Yeah. Okay.
So even here, as we naively would think that dimensional analysis would fail if we had eta, we had to supplement it with this lambda.
You can calculate mu, right? Or mu c at critical.
Yeah, we find the mu c at the critical point, but plug it back in here, but it's meaningless. That's the idea.
Yeah, you can calculate that. That's right. You just have to do whatever we did last time, I guess.
You can calculate it up to lambda. You can calculate this ratio, or y you can calculate, I think.
Yes.
Yeah.
But it doesn't necessarily mean anything plugged in here.
Yes.
Yeah.
Right. All right. Now we have that. Now the next thing, we'll do some bookkeeping things again. So recall we do this step under RG, and we also said that under that step, phi goes to phi prime with some scaling. Right? We did this to ensure that this kinetic term didn't scale. But now if phi has this, not just naive dimensions, but this extra dimensional analysis failing bit, then we have to adjust for that in the scaling, which is simple. So just try it here. If I just scale it, you would get zeta to minus 2 delta phi should be equal to, scale it here as well, which is 1 by zeta inverse to the power d minus 2 plus e. Just scaled both sides. So under scaling, this should not change. So that gives us that the phi is equal to 2 minus d minus eta by 2. Just fix the scaling of phi because we will need it. Now, the next thing. Yeah, this is a thing that we just mentioned. If we move away slightly from the critical point by tuning y, then we get a new length scale other than the cutoff, which is the critical, not the critical, which is the correlation length, which is ultimately coming from the temperature, right? So away from PC, length scale C. right? And at the critical point, we must have c going to infinity. So let me define some quantity which is just the difference of the temperature from the critical temperature divided by, it's just dimensionless ratio. Then if we want correlation length to diverge at critical temperature, we must have some sort of relation like this, right? And correlation length would diverge under T going to Tc. However, no, let me say something. Yeah, also remember that T is like mu square, right? Mu square we discovered is proportional to T minus Tc to describe these phases. And under scaling, mu square changes. So it's not a wrong question to ask, under scaling, how does T change? It seems to be obvious because, T should change exactly like this. But remember that this only did these two steps. The extra step might introduce something new, which we will discover from just this equation soon enough. But let's just, in general, say that under scaling, T goes to zeta to some scaling dimension T, and tentatively delta T must be minus 2. At least in the D equal to 4 case, delta T should be minus 2, right, to recover this. And correlation length being a length must scale like a length, right? So immediately, this will give us new in terms of the scaling dimension of this reduced temperature, as we call it, or the scaling of mu itself. We can just find it by scaling this and find that zeta inverse, that's the scaling of C, should be equal to zeta minus delta T to power minus nu, right? And that gives us nu equal to minus 1 by delta T. So let me put that down here. So we have C diverging, and that's nu equal to minus 1 by delta T. If we compute the scaling, we immediately computed another critical exponent. All right, let's now think about the other exponents.
I'm a little confused. What mu squared? So mu squared changes under this RG flow by parameter zeta, right? But why does T do that? I thought T is just a property of the microscopics.
Yeah, so
whatever the actual temperature is, and Tc is whatever the microscopic dictator should be.
yeah, so I should just write it like this, I guess. So T is just a dimensionless thing. Yeah, we are essentially just finding how mu square changes, not like, by T is something that you're tuning, that the temperature in the knob that you set in the knob shouldn't change under RG, but mu square definitely does. Yeah, so this is probably more appropriate, right?
So I'm trying to understand what's the definition of this critical critical exponents are.
Right. So
what's the common feature between all these critical exponents?
the common feature, roughly speaking, is that some quantities, for example, correlation length or heat capacity or susceptibility, all of these diverge as you get to the critical point. So the divergence should be characterized by T minus Tc to some power, right? The divergence is under when you go from T to Tc. And these powers are the critical exponents.
So that zeta goes as or as a phi going to phi prime.
Mm-hmm.
That you have defined as under some sort of coordinate transformation.
Yeah, so x going to zeta inverse x imply this. So the reason was to, oops, I erased, to keep the kinetic term doesn't change units. Yeah, or dimensionless. Yeah.
So how are we approaching? How do I see that you are approaching criticality in this?
From here, it's not. It's just for later use that I did it. But here you can, right? So when t goes to Tc, this goes to 0. Then correlation length diverges. So here you see it. But people also call this a critical exponent. The reason I think is, as we will see now, that we will only use eta and nu and compute everything else. So
for now, eta is not really related to as you approach criticality or something like that.
Yeah, eta is actually defined at the critical point.
Yes.
So should the numerator, when you have t equals absolute value of v squared over tc, should it be like v squared minus the value at the Wilson-Fisher point or something?
Yeah, I think that is correct.
Okay, yeah, 'cause then that would
That's
be your
correct.
sign.
Yeah. So how would I write it? So mu square minus mu square critical. Yeah, something like that. Yeah. Yeah.
Yeah.
Right. So was that clear? So this is where the divergence bit is coming in, but people also call this a critical exponent, which breaks the pattern as we just discussed. Okay, the next critical exponent, if you remember, was the heat capacity. Yeah, this can be a bit confusing though. So to find heat capacity, we want to look at the thermodynamic free energy. From that, you can compute heat capacity. But if you are slightly away from the critical point, then you have this correlation length c, meaning spins are correlated at distance c, right? So you can approximate the whole system into, roughly speaking, blocks of size c, and within each block the thermodynamic free energy is not changing. So overall, the thermodynamic free energy could be approximated. We don't need the detailed answer, we just need the scaling. So we find the thermodynamic energy for a block of size c times number of blocks, which is total volume divided by volume of a block, right? So we can just plug this thing in and then see that this goes like L to the D, some number, T to the D. And then we define heat capacity per volume. We again don't need the details, we just need the scaling as 1 by volume, the second derivative with respect to T, because T goes like temperature or difference in temperature. And then we get this to be going like T to the D nu minus 2. Very simple. But heat capacity diverge like T to the minus alpha by definition. So we get alpha equal to 2 minus T. So we have another critical exponent, C, that diverges like T to the minus alpha, but alpha is 2 minus D.
So you redefine T to be independent of temperature over there, right? Initially you wrote that as T minus Tc. Now it's mu square minus Tc. You're taking derivative with respect to
mu square.
temperature.
Yeah, I'm confused about that. Should be with respect to temperature.
So you tune temperature to mu.
Mu, yeah. So to leading,
mu squared is goes linear.
Yeah, which we already assumed to qualitatively describe the phases, right? So mu square minus mu c square must go like T minus Tc to have this order and disorder in D equal to 4 case. Okay. I don't know. It's the computer. Okay. Yeah.
So you have to assume that it's not like it doesn't go like square root of 2 minus
Yeah.
C or something, or cube root of 2 minus C.
Yeah. So the assumption was, right, mu square is analytic function in T. So we Taylor expand it near the critical point, but we cannot have a constant term because that wouldn't describe the sign change of mu.
Do we not have a constant, or is the constant just mu sub C?
Oh yeah. I'm still thinking of the Gaussian. Yeah. So mu C plus T minus Tc stuff. So, hand waving. Do chain rule or something. Differentiate with mu.
This calculation is near the criticality.
Yes. It's very close to critical point.
So then higher order terms are written.
Yeah. That's what we assumed, but as you said, it's a bit sketchy. But all of this is sketchy in some sense because we are, doing all of this in the squiggle level.
I'm a little confused though, because how does because we're looking at how this changes when you change zeta, or you do this flow by zeta. So mu squared is supposed to scale in some sense. But T can't change. T is just the temperature, right? And Tc also
It's fixed.
change.
Yeah.
It's just 0.6 or something times
Uh-huh.
J for the Ising model.
Yeah.
Whatever. So there's some conceptual disconnect in my mind about what's going on here.
Yeah, I agree. Yeah, if this was d by d mu square, then that would have made sense, but it isn't. It should be d by t, d by dt square, like t square.
So what's the problem?
Because to get this relation, we have to differentiate with respect to small t.
Yeah, but before that, since mu squared is related to t, then that should hold, right?
Why some chain rule, something like that? That are you saying?
Yeah.
It's just a conceptual disconnect, as Gary was saying, that mu, this is supposed to be like mu, but we are differentiating with respect to temperature, which is related to mu, but under Rg, even though mu is changing, T is not changing. So I guess you stay here somehow, very close to critical point, and not think about running to infinity, I guess, somehow.
So what do you mean when you say that mu is changing but t is not under R? Does that mean that on this plot, like t is defined at all points on this plot?
Yeah, T is some external parameter, right?
That doesn't. Okay.
But mu depends on this external parameter.
Yeah, but so in that sense, if you have a mu, you know what t is.
If you also know the zeta, right?
You also know the zeta.
Also know this.
So it seems like zeta is not only a thing, it's not a value.
Yeah. It's just
Because it's not like zeta determines the cutoff scale or something. We scale it.
yeah.
So zeta is just something you can do a flow by amounts.
It's a parameterization. Yeah.
But if you flow by zeta, if you start at some mu that's not at the fixed point, it's a little bit above or below, and you flow zeta,
Then you just flow to infinity.
plus or minus infinity.
Yeah.
So
It is conflated in the sense that you want to sit close to here, but also use zeta. But then that's
right.
Yeah.
So if I'm at t that's not tc, but it's close to tc, then what is mu? Well, I could say it's right over there on that plot, but then I can flow by zeta and it's somewhere else. Right?
Yeah. So I guess you sit close to the critical point, but flow by a very small zeta that's extremely close to 1. So after flowing, you also get here. But that's enough to describe the scale.
Mm-hmm.
Maybe that's the argument.
So then, okay.
In that approximation, mu is just temperature. And then I can differentiate with respect to temperature and then call it as a differentiation with respect to mu or small t.
Mm-hmm.
So in that case this holds, and that's all we need, because we are tuning T to TC anyway.
So
I'm just making all this up.
Yeah, it's weird. When you make those arguments, you have to. It's like you're thinking that you have some finite. So when you're not at the critical temperature, then zeta infinity just takes you away from it. But you're kind of assuming that you don't take zeta to infinity. You take zeta to some finite value, and at your experimental energy scales, and then you do your scaling arguments. So you don't know for first of all what finite value of zeta you're taking it to. It's just that you take it to be whatever it is, so that you're close to the critical point, I guess.
Yeah.
Which is kind of weird, but
Yeah.
it's fine.
Yeah. For the argument's sake, to discover this, I think it's kind of fine. But how do you justify it? Always is the question, I suppose.
I guess you just have to be careful what you say. And I don't know how to carefully say it.
Say this, yeah. Me neither. Yeah.
I think derive the flow, we need to assume that this zeta 1 plus s.
Yeah. Zeta is 1 plus s. Yes.
So that an s model is going to be small. Right?
Yeah.
So,
But then we are extrapolating. Also, don't forget that this is linearized and so on. So this should be trusted, very close to the point. So maybe even if zeta is large, T minus TC is so small that you need even larger zeta to run to infinity. So yeah, again, that's a repackaging of whatever we just said now.
yeah, so do we need delta sub t for anything?
Yeah, we need that for everything, basically. From that, we compute all of this.
What I'm saying is, I mean, it ends up just being -1 over nu, right?
Yeah.
So can we just eliminate it from the conversation?
In principle, yes. Yeah.
That might actually be a little bit clearer. We don't have to talk about t scaling under zeta.
Yeah, but the way I prepared today is to compute eta and delta t, and then from that derive everything.
So how do we compute delta t?
That's from here.
Okay.
Again, delta t is understood as scaling of mu square. Yeah. So I think this is the correct thing to imagine as we are doing, but then this becomes sketchy.
Yeah.
Yeah.
In the notation that I'm more used to, it's the other way around. T is just small t is just capital T minus TC over TC. And then that definition of peak capacity works fine, but you don't relate that to how do you relate it to this? You don't really relate it to mu squared, I guess.
I mean, you must relate it to some mu square, otherwise you cannot find anything from this flow relation. So even in this 2D CFT business, what you find is just scaling dimension. And then from that, you just use this. This works for any D. And then, so we are probably missing some conceptual
I think
thing.
so. I mean, I didn't. I don't remember looking at it in this context. It was just D was 4 like from the beginning. The 4 greater than 4. So, but I don't. I have to think about it. But this is tricky.
Yeah.
Something is there is some conceptual disconnect.
Yeah. If D is 4, then we don't have to go through these arguments and we can compute all of them individually, one by one. But this is much faster. And it works for 3.9992. Yeah. So even if we derived it in a sketchy way, I guess maybe this can be derived in a different way. This is called Fisher's identity. So he must have a different way. I should check he has a set of lecture notes on RG. That must have it, I think. I would check it again.
These, if I remember correctly, you can get a lot of these relationships by just writing these expressions as functions. I think of the ratios of the various length scales like L and C, and then doing some sort of assuming they have power law forms near 0 and infinity, and then expanding.
Yeah. Which is something like these arguments, I guess, but yeah.
So F block of size C is constant.
Yeah, because the spins are correlated. That's the argument. So you can just find the.
Yeah, but its block size it's bigger than you have more spins, so your free energy should go up.
Yeah, so for a fixed C, we're talking about that in a fixed C, right? So yeah, that again requires that we sit there at some point.
For fixed C, sure. And then times the number of blocks. But
Yeah.
you're not changing C though, right? Because you're not fixing C, you're changing the temperature.
Yeah, I guess what we have assumed is, we change temperature, but somehow.
Your L will be fixed.
Yeah. L is fixed, of course. And, you're sitting here, not running. Then C is fixed. Then up to this argument that holds.
No, C is not fixed. It goes to it diverges as you take T changes sign, right?
Yeah.
So because we're trying to find the dependence of F thermal on small t, so C can't be fixed.
C cannot be fixed. No. I can fix C, right? Just change temperature to, a little bit away from TC and then stop. And assume that RG running is not happening.
So you change from infinity to something finite.
Yeah.
Which is a big change.
Yeah, and then stay there.
Okay.
And at that temperature, you have a C, and then this is the answer.
Yes, but what I'm saying is, in the steps you wrote, what we're computing is F thermo's dependence on T, right?
You mean the derivative?
Well, then we compute the derivative. First, we calculate F thermos, and then we just differentiate it twice. But you can't compute that dependence while assuming that T is constant. So
I agree.
If you can't assume T is constant, then this C is not constant. Which means taking that F parenthesis block of size C and just absorbing that into that hashtag doesn't seem to follow.
I agree on that.
Yes.
Yeah, but I don't know how to. Should look at Fisher's textbook, I guess. But
maybe
this is correct.
Maybe it's very slowly depending or weakly dependent on C.
So yeah, so if I remember Chern's thing correctly, I mean, it might take me a few minutes to repeat this.
Yeah, I guess we'll come back to this at the end while Gary figures it out. The take-home messages, even though the argument is extremely hand-wavy, the final answer is correct.
Okay.
So that's that. Let's find another critical exponent. Yeah, the other critical exponent was, let me not erase this. How the magnetization, average magnetization goes to zero or diverge close to the critical point. So that would be how phi changed with t going to tc. So this beta was another critical exponent. So phi went to t beta. But here is what we can make use of this delta phi, scale this, and then we get zeta minus delta phi. That's how this side scales. And from here we get delta t beta. And then we get beta is delta phi by delta t. That's 2 minus d minus eta by 2 delta t. So beta is the next one is when we turn on magnetic field and look at the susceptibility. So when we turn on magnetic field, we add this term. But this term also should be scale invariant, so we can say how this parameter scales from this. So we get under scaling zeta to minus d from x, zeta to minus delta b for this guy, let's assume zeta minus delta phi should be 1. And then that would tell us delta b is minus d minus delta phi, which is minus d minus 2 plus eta by 2. And then we can just compute Susceptibility is scaling. Susceptibility is change in magnetization as you change external magnetic field. And this is by definition supposed to diverge like gamma, another critical exponent, t to the minus gamma. Scale again, we get zeta to minus delta phi plus delta b on the left side. That should scale as zeta to minus plus gamma delta t. So gamma is delta b minus delta phi by delta t, which is, if you do the math, 2 minus eta by delta t. There is another one, the last one,
What is B phi?
d phi.
B times phi is what entity is done?
Oh, so to introduce magnetic field, we need to add this term to the action.
Okay, right.
Yeah. So this is the external magnetic field coupled to spins. And if we do the last one, which was how at t equal to tc, phi changed with b. So the definition of that critical exponent is like this. Again, a definition. So if you're at tc and then change b, how phi changes or phi diverge or have a cusp in it or something. And this again, by scaling, we get zeta minus delta phi should be the same as zeta minus delta b by delta. So we get,
Why is this not the susceptibility?
no, susceptibility is this, right? Rate of change.
And what is this other one?
So this is, this was the definition of how chi diverged under t going to tc. So this is, you fix t equal to tc and then change magnetic field. So you think how average magnetization is changing. Yeah, so this would give us, well, the last one as phi b to the 1 by delta. Delta will be whatever this is. Delta will be delta b by delta phi. Plug values in, so we get p plus 2 minus eta by p minus 2 plus eta.
I think the magnetic field has the same issue as temperature, as in like why should it scale with scaling?
Yeah, I'm still confused about that now. So this must be true, otherwise this wouldn't stay. This is dimensional analysis basically. So this is what's the dimension of magnetic field, and this must be true. And what we are doing essentially is dimensional analysis in that sense.
So when you go to different energy scales,
So when we change x to x prime equal to x by zeta, we are changing units of length.
yeah.
So in that sense, the units of temperature should also change.
I'm asking like why should like maybe you're defining new notion of magnetic field and temperature in that sense.
No, you're changing meters to centimeters, so magnetic field changed something.
But it's like psi to the power some zeta is dimensionless.
Yeah.
Alright.
So you change units, so when changing units, it gets multiplied by a number, right? Kilometer to mile is 1.6 or something.
Is it like this averaging effect? You measure magnetic field at this location, but when you are scaling, you are just measuring an average magnetic field over a large region.
That's roughly the picture in some sense.
So
That-
is the scaling related to this averaging process?
Yeah, the scaling was related to the zooming out, right? So we first integrated out high energy modes, and then we changed x to x prime so that it matched units with the original theory. So after you integrate it out, you've lost many modes or lost small distance modes. So you are measuring the effective thing.
So now you're measuring effective temperature and time effective.
Yeah, I think that's correct. And changing units of position would change units of temperature, makes sense. But does that fix this problem though? The conceptual problem?
No, I don't think
Yeah. No, but that fixes the scaling of T minus Tc by Tc, right? We are changing units. So T minus Tc also should change units from kilokelvin to Kelvin. Well, it's dimensionless, by the way. So
yeah, the little t is
yeah,
dimension.
yeah. Yeah, that's still confusing.
But still, like DC won't change under scale. Right?
Tc,
Won't change under.
but if you change units again, right?
No, if I'm just taking scale as an averaging process. DC is a defined temperature.
Yes.
Now, if you average it over a larger space, still it's DC is a constant.
Yeah, I see what you're saying. But the external temperature is also something that's set by you, right?
Yeah. It does average out to something. It can average out to something else than a point, rather than what it was at some point.
Oh, I see what you're saying.
I don't know. I'm just making guesses.
Yeah, we're all making guesses at this point. So, yeah. It doesn't fix this conceptual issue, I think. But it almost fixes the conceptual issue that why it may fix the conceptual issue why small t scales. But I'm confused about the dimensionless bit. Yeah,
You can think about it.
yeah. Gary's figuring it out, I think. So you'll know by the end. Right. So the whole point of this exercise is maybe there's a proper way to derive all this, but David Tong does it in this cheeky way. And the point is that since all of the exponents are related to each other, we just have to find any two. So if we find eta and nu or delta t equivalently, we find everything else. So we just find it now. So let's do first d equal to 4. So we first need to find, let's say, eta, and that comes from the correlation, right? So correlation at t equal to tc. So the correlation phi x phi 0 is integral d4k 2 pi 4. This correlation function at the Gaussian comes from the kinetic term, of course, e to the I k dot x 1 by k square plus mu 0 square, but mu 0 is 0 because we are fixed at tc, k square. Now we can compute it or do dimensional analysis, right? Because this is dimensionally k to the 4 by k square, goes like k square, and the only dimension full parameter is x. So it must go like 1 by x squared, right? Which is equal to 1 by x to the power 4 minus 2 plus 0. So we found eta. Eta is 0. Now we find delta t. So delta t, as we are confused about, is the scaling of mu square, right? Which we can understand from here. So take epsilon equal to 0, so that we are at d equal to 4. You have a question? Then the differential equation becomes delta x, delta y equal to 0, 0, 1, 2, delta x, delta y. We can diagonalize this by defining q1 equal to 2 delta x minus delta y, which is this direction, and u2 equal to delta y. I mean, we did this last time. And then d by ds u1 u2 is 0, 0, 0, 2 u1 u2. It's a diagonal matrix, so you can solve this differential equation very easily. In particular, u2 of s is e to the 2s u2 0. Eigenvalue to power e to the s, but e to the s was zeta, so we have zeta square u2 of 0, right? And u2 is y, and y is mu square. So ultimately, this tells us that mu square zeta is zeta square mu 0. Nothing new, right? This is the naive scaling. So that tells us, this should be zeta to minus delta t mu square 0 delta t equal to minus 2, as we anticipated already. Plug that in to get nu equal to half. Now it's just a plug-in game. So let's plug in for alpha. Alpha equal to 2 minus 4 by 2. That's 0, right? I think that's correct. 2 minus 4 by 2 is what? 2 minus 2 is 0. So that's correct. So beta is equal to, okay, that's hard. Eta is 0. 2 minus 4 by 2 minus 2 gives us minus 2 by 2 minus 2 gives us 1 by 2. Plug in for gamma. That's minus 2 divided by minus 2. So gamma is 1. And delta is 4 plus 2 is 6 by 4 minus 2 is 2. So that's delta equal to 3. And if you numerically simulate the Ising model for d equal to 4, you actually get it, which is fine. This was not of our primary interest. We wanted to know if Wilson-Fisher point is the correct point in d equal to 3, even though we don't have access to d equal to 3. So now we go back to 3.99 and see what we get. .99. Then what we need is, first we need eta, but once again eta is going to be 0 to this order. The reason being, as we mentioned earlier, the need for eta comes after the third step of RG where we change the units of phi. But in the one loop order that we computed the diagrams, we didn't have to do that step. If we go beyond one loop and go to two loop, then eta will be non-zero. So
This integral is always d minus 2. That integral has a dimension of x power d minus 1 over x power d minus 2.
yeah, so this integral will give you just that. The only thing that can change the scaling is rescaling of phi itself, which was the third step of RG, which we didn't have to do for one loop. So we are guaranteed that eta is 0 plus order epsilon squared. The non-zero value comes next order when we do two loops. Then we need delta t.
So why is the loop counting the epsilon counting? I don't remember.
Yeah, the loop counting is not the epsilon counting. Epsilon is a separate
Counting is the
expansion.
Small lambda counting. Right?
Yeah.
And
So we said something about it last week, why loop counting correlates with epsilon, but I cannot remember now. Yeah, why was it so?
maybe the small lambda the next order in small lambda has a small epsilon.
No, the epsilon comes from just d minus epsilon, right? Yeah, we need lambda to be small for perturbation theory to be true, of course. And then this Wilson-Fisher point is self-consistent so that it has small lambda. Yeah, something along those lines is the argument that I cannot quite remember. So if you want to go higher in epsilon, I think you have to go higher in loops too. If you just stay in one loop and go to higher in epsilon, then that's somehow inconsistent, which I would check. And
yeah, I guess because they have two small parameters.
yeah, I cannot remember the argument.
Epsilon squared is smaller than epsilon. Right.
So I'll explain this next week because we had it last week. At the end, I think you yourself said the argument.
I don't remember.
Yeah, I don't remember it either.
I mean, we have the videos.
Yeah, yeah, you can check the video. Or next week, I'll try to sort out this puzzle as well. Both the puzzles. Right. So the next thing we need to compute is delta t, which again comes from here. We can use the same change of basis and find that d by ds u1 u2 is equal to minus epsilon 0 0 2 minus epsilon by 3 u1 u2. So we see that u1 is irrelevant in the sense that u1s is e to the minus epsilon s. u1 0, it goes to 0 as we increase s, but u2 is e to the 2 minus epsilon by 3 s to 0. And u2 was y was, u2 by the variable change is y was mu square was temperature. So from this we get delta t equal to minus that. So we get minus 2 plus 1 by 3. Now let's plug and chug. I'm going to just write down the answers. So we have alpha equal to, plug in here, epsilon by 6, beta equal to half minus epsilon by 6. Everything is obtained from here. Gamma is 1 plus epsilon by 6. Delta is 3 plus epsilon. Of course, everything has to be close to whatever that is because epsilon is small. And nu is half 1 plus epsilon by 6. Higher order epsilons are ignored. And eta is 0 plus 0. Okay, but that's 3.99. What we are interested in is actually 3. But we cannot use this for 3, right? Because we assumed epsilon is small, and that only adds phi 4 as a relevant parameter, but at 3, phi 6 comes in as a relevant parameter, and so on. But we will be just careless, plug in epsilon equal to 1. So epsilon equal to 1. This is a naughty thing to do. And we get the following values. Alpha is 0.16, beta is 0.33, gamma is 1 by 0.16, delta is 4, nu is 0.58, and it is 0. But the funny thing is, people have done experiments on the 3 equal to Ising model, and the values are 0.11, 0.33, 1.24, 4.79, that's a bit bad, 0.63, 0.04.
What's the error?
The error in the experiments? Of course, I don't know.
Is it like of the same magnitude as these numbers, or is it like 0.11 plus minus 0.2?
I don't know. I would assume that the last digit is not known.
It's just the last digit.
Yeah. So people have done this epsilon thing to higher loops and got answers closer. Yeah.
On which side, the middle one?
The middle one.
So
Of course, you have to do it here and then epsilon equal to 1.
So these numbers in the middle column get closer to the experimental one.
The take home is that we are hitting the Wilson-Fisher point in the equal to 3 Ising model, even though we don't know what the Wilson-Fisher point effective field theory is. We can start from an effective field theory that doesn't work in the Wilson-Fisher point, but from that, by doing this analytic continuation, discover the Wilson-Fisher point, and it's embarrassingly quantitatively roughly correct. I don't know what to make of this though. Is it always true in every model? I don't know. I know that it's true for Ising, and I know that it's true for this Heisenberg magnet, for example. Yeah.
So when we write the theory, or write the Hamiltonian, why do we have to consider all possible terms?
Yeah, the point is that this is an effective theory that we are writing down, and we do not have a God-given theory. So we just write down everything that's allowed under symmetry.
What if there are certain terms like phi 6 pieces they, even though they are relevant, but they're just not there.
What if it's not there?
Yeah, I mean, we are assuming all the terms that should be there.
Mhm.
What if it's just not there? I'm just making a very vague argument.
Yeah. So remember that this Ising model theory is supposed to work for anisotropic magnet of any molecule and liquid vapor system of any molecule, for example. So you have practically a large class of theories for which this works at the critical point or close to the critical point. So you cannot make the argument that for all the large class of arguments, this G6 term is 0. It's generically something for everything, but if you're at d equal to 4, it just doesn't matter. It's irrelevant and it's driven to 0 by RG automatically. But at d equal to 3, it is relevant. So you cannot use this scalar field thing that we did at the Wilson-Fisher point. But at d equal to 3.99, you can still use the scalar field thing.
So they have done this experiment for d equals 3 Ising model. Does it also work in other models for which you apply the theory in 3 dimensions?
Yeah. So if you do this experiment for liquid vapor system, you get these answers.
You do get these answers.
Yeah. You can do it for carbon dioxide. I think people have done it. For water, I don't know. People must have done it, but yeah.
I don't know if they get the same answer.
They get the same answers. So these are said to be universal. It's a fundamental constant.
We have to come up with a reason why phi 6 is not important.
No, phi 6 is important if we use the effective field theory that we started off with. The idea is that the effective field theory that we started off with do not work at the Wilson-Fisher point. So if you want to keep using the effective field theory that we started off with, we have to stick at 3.99. But so this is true. But we did something naughty and that also kind of works. I don't know why though. Yeah. I don't know what it means either.
Yeah, because since we have gone into philosophical, I was just thinking like the issue was in d equals 3 that phi 6 term becomes relevant and you cannot in general get rid of it.
Yes.
Or is there any other issue?
This is the issue. Phi 6 is relevant, but you only have temperature to tune. So you cannot tune two parameters at the same time. If you are only tuning one parameter, then typically you are at some random point in the theory space. But if you are at some random point, then you just run to infinity. You never hit a critical point.
Yeah, but then like it's our desire for it to be a general theory. Phi 6 term should be there.
Yeah, if it worked, then if you had two parameters to tune.
I'm saying like let's say all the application of this theory in 3 dimension gives the same critical exponent. Will it be suffice to say that the phi 6 term is not there in all these theories?
I don't know. I don't think that's correct either. Yeah, because you typically expect some random value, right? Because you have many theories, and these couplings represent some microscopic detail of the system, and it should change typically for different microscopic systems. They are different in the microscopic details. But the point is that close to critical point, these microscopic details have washed away. And you can use an effective field theory to describe the system. But can we construct an effective field theory is a different question. For d equal to 4 and 3.99, we can construct an effective field theory. But d equal to 3, we cannot explicitly construct an effective field theory. So we shouldn't think of d equal to 3 being described by phi 6 theory. It's described by something that we don't know. but we used what we know and then tried to extrapolate it to the case where this thing shouldn't work, but still that gives something close to reality. What do you make of this? Yeah. Make of this as mathematics is rubbish, just hand wave all the time. Yeah.
In that sense, I feel like then in gravity, although it's not an effective field theory,
It is, right?
that we don't use all the possible terms.
You don't, but there are, well, if you expand gravity around flat, then you have infinitely many interactions. So you would have infinitely many irrelevant terms. That's why people say you cannot renormalize it, meaning you cannot take it to UV. But in the IR, everything is fine. All these irrelevant things are gone, and then you can use gravity classically. So non-renormalizable means that in the action you have irrelevant terms. So these are irrelevant for IR, but they are important for UV, right? So this universality is a curse to know the UV physics. We can only observe physics experiments in some energy scale, and if we want to know the theory beyond that energy scales, there's just no way. So you can try adding irrelevant operators to see some signs of that in the experiment beyond standard model or something. Yeah. Or beyond general relativity too, of course. Yeah. So the idea is this, adding irrelevant operators to see signs of it. And then you can guess. Micho's talk was basically that. They would add an irrelevant operator and then put a bound on the coupling and then try to come up with a UV completion, which if you integrate out some extra additional degree of freedom, you get this theory with irrelevant operators. Yeah. But this is specific to statistical systems where you can actually tune something. For quantum theory, you're not tuning anything, right? It's the ultimate being that tunes anything, which doesn't exist.
So is it that physicists just like analytic functions, or
Yeah, I think that's the
reality analytics? And why even people, or why is reality supposed to be described like complex analysis?
excellent question.
And the necessity here would be in the dimension.
No, the action functional that we wrote, we assumed it's analytic in phi.
Yes.
Yeah, because that's the only thing we know how to do. We know Gaussian integrals and differentiable functions.
There is an argument for that. I don't remember how good the argument was, but there's an argument why it should be analytic, having to do with if the if you have if the interactions are local, decaying rapidly enough, and I don't remember how that goes.
So it has something to do with interactions supposed to be local.
But also, there is this I don't know if it's non-analytic. There's this Coleman-Weinberg thing, right? They get a log of phi or something in their action by doing some RG one loop renormalization.
And they get a log of
Log of phi, I remember. Or is it log of 1 plus phi? I don't remember. It's log of 1 plus phi. Okay, I give Taylor expanded. If it's log of phi, then it's non-analytic at phi equal to 0. So it's not always analytic, if I'm not wrong, but I have to check Coleman-Weinberg again.
You know what else is log of 1 plus something? Tune in the archive. Oh, that paper's already on there. No. Oh, because
So next week, what I think is I tried to rectify this confusions. One about epsilon versus loops, and the other one about the hand waviness. And I think I will just recap everything from start to end as a summary so that we have, a checklist. Well, we know the summary. The details are in YouTube. Yeah.
Diva's one page
Summary, something like that. Yeah. And then end with a cliffhanger or something. Yeah.
we already